In this chapter, we zoom into data distribution and distributed transaction management. It is based upon our book, Principles of Database Management, published by Cambridge University Press. You can find more information about our book on the website at the bottom of my slide. My name is Bart Baasens, and I'm one of the authors of the book. In this chapter, we focus on the specifics of distributed databases. First, we discuss the general properties of distributed systems and overview some architectural variants of distributed database systems. Then, we tackle the different ways of distributing data over nodes in a network, including the possibility of data replication. We also focus on the degree to which the data distribution can be made transparent to applications and users. Then, we discuss the complexity of query processing and query optimization in a distributed setting. The next section is dedicated to distributed transaction management and concurrency control, focusing both on tightly coupled and more loosely coupled settings. The last section overviews the particularities of transaction management in big data and NoSQL databases, which are often distributed in a cluster setup, presenting base transactions as an alternative to the traditional ACID transaction paradigms. A distributed computing system consists of several processing units or nodes with a certain level of autonomy, which are interconnected by a network and which cooperatively perform complex tasks. These complex tasks can be divided into subtasks as performed by the individual nodes. By dividing and distributing a complex problem into smaller, more manageable units of work performed by semi-independent nodes, the complexity becomes, at least in theory, more manageable. This makes the system also more scalable. Distribution of data and functionality often guarantees a certain measure of local autonomy and availability. Distributed database systems distribute data and data retrieval functionality over multiple data sources and/or locations. Part of the additional complexity is because most distributed database systems are designed to provide an integrated view of the distributed data. They attempt to offer a certain measure of transparency to users and application programs. This transparency refers to the often desirable property that the user is insulated from one or more aspects of the distribution. A distributed database environment may emanate for different reasons. First of all, it could be a deliberate choice. However, more often than not, distributed architectures are merely a consequence of other factors, for example, a merger or acquisition, or simply consecutive investments in different database technologies for technological and/or financial reasons. If data distribution is a deliberate choice, one of the main concerns will be to decide on optimal distribution criteria. Example criteria are performance or local autonomy and availability. Other important elements are the degree of transparency that is to be offered with respect to the distribution, how to deal with distributed query processing, the complexity of distributed transaction management, and distributed concurrency control and recovery. Particular to distributed databases is that the data and DBMS itself are distributed over multiple interconnected nodes. Within this realm of systems, there are still different possible architectures. In a shared memory architecture, multiple interconnected processors that run the DBMS software share the same central storage and secondary storage. As more processors are added, this shared central storage may become the bottleneck. With a shared disk architecture, each processor has its own central storage, but shares secondary storage with the other processors. The disk sharing can be realized by, for example, a storage area network or network-attached storage. Shared disk architectures are typically more fault-tolerant than shared memory architectures. However, a possible bottleneck is the network that interconnects the disks with the processors. The most prevalent approach for distributed databases is the shared nothing architecture. In this setup, each processor has its own central storage and hard disk units. Data sharing occurs through the processors communicating with one another over the network, not by the processors directly accessing one another's central storage or secondary storage. You can see the various architectures illustrated here. Scalability can be achieved in two ways in a distributed database system. Either the capacity, such as CPU power or disk capacity, of individual nodes can be increased, which is called vertical scalability. Horizontal scalability is achieved by adding nodes to the system. Here, the challenge is to keep the coordination overhead over the respective nodes as low as possible. NoSQL databases can achieve near linear scalability, whereas traditional standalone databases are restricted to vertical scaling. Horizontal scaling of distributed RDBMSs may be problematic beyond a certain number of nodes because of the increased coordination. However, reducing coordination overhead to improve horizontal scalability may also come with a cost in terms of less consistent data. Some authors distinguish between distributed databases and parallel databases. With parallel databases, they refer to data distribution with only one purpose, performance. The performance gain is achieved through parallel access to the distributed data. We can distinguish between intra-query parallelism, different subsets of the data are searched in parallel in the context of a single complex query, and inter-query parallelism. Many simple queries are executed in parallel. Parallel databases can have a shared memory, shared disk, or shared nothing architecture. In what follows, we will use the broader term distributed database and will not use the term parallel database. Furthermore, it is worth noting that if the respective nodes in a shared nothing architecture each run an independent DBMS instance, and if the data are fragmented horizontally over these instances, the term federated database is often used. Fragmentation refers to the partitioning of data into subsets, also called fragments, based on performance, local autonomy, and availability. We can distinguish between vertical fragmentation, horizontal fragmentation, and mixed fragmentation. With vertical fragmentation, every fragment consists of a subset of the columns of the global dataset. Vertical fragmentation is especially useful if only some of a tuple's attributes are relevant to a certain node. The vertical fragments contain the necessary columns, most often the primary key, to combine the respective vertical fragments with a join construct if a view of the global dataset is required. According to horizontal fragmentation, each fragment consists of rows that satisfy a certain query predicate. In this way, network traffic for queries on local data is reduced and local availability is improved if network failure occurs. A global view can be reconstructed with a union query over all the horizontal fragments. Horizontal fragmentation is also applied in many NoSQL databases organized in a cluster setup, where the horizontal fragments, called shards, are attributed to different nodes in a cluster. Finally, mixed fragmentation combines both horizontal and vertical fragmentation. A global view can be reconstructed by a query containing join and union operations. Here you can see both horizontal and vertical fragmentation contrasted. Here you can see the result of vertical fragmentation, whereby one node is responsible for order processing and only needs the customer IDs and customer names, whereas the other node performs data analytics on the customer data and is mainly interested in demographic data such as country, year of birth, and gender. Here you can see the result of horizontal fragmentation, where the rows are attributed to worldwide nodes according to the country of the customer, so customer data for each country can be stored in the local branch. Here you can see the result of mixed fragmentation, where rows containing customer ID, first name, and last name are fragmented horizontally according to the customer's country. However, there is also vertical fragmentation, since all demographic data are allocated to a separate node to perform analytics on worldwide customer demographics. Sometimes derived fragmentation is applied, which means that the fragmentation criteria belong to another table. For example, the customer's data can be fragmented according to the sales total for that customer as stored in a separate sales table. Data distribution entails the partitioning of the global dataset into smaller subsets called fragments, which are then allocated to individual nodes. The subsets may or may not be disjoint. If the subsets overlap, or if there are multiple identical subsets allocated to different nodes, we have data replication. There may be different reasons for data replication, such as local autonomy, performance, reliability, and availability. Replication also induces additional overhead and complexity to keep the different replicas consistent and propagate updates to a data item to all its replicas. Similar decisions as the ones on the distribution and replication of the actual data need to be made with respect to the metadata. Will all metadata be centralized in a single catalog, or will the metadata be fragmented and allocated to, for example, the nodes that contain the data described by the metadata? Also, there is the question of whether some metadata must be replicated, for example in a setup with both local catalogs and a global catalog. Replication is often desirable, since only a single global metadata catalog has a negative impact on the local autonomy of the database nodes, whereas only local catalogs make it hard to perform global queries and interpret their results in a consistent manner. Of course, if global and local metadata catalogs exist, their consistency needs to be assured over time as well. Transparency refers to the fact that, although the data and database functionality are physically distributed, the application and users are confronted with only a single logical database and are insulated from the complexities of the distribution. In this way, this transparency can be looked upon as an extension to the logical and physical data independence. An important property is location transparency, which means that database users do not need to know on which node the required data resides. Fragmentation transparency refers to the fact that users can execute global queries without being concerned with the fact that distributed fragments will be involved and need to be combined to perform the query. Replication transparency means that different replicas of the same data item will be automatically kept consistent by the database system, and updates to one replica will be propagated transparently, be it synchronously or asynchronously, to the other copies of the same data item. Access transparency refers to the fact that the distributed database can be accessed and queried uniformly, regardless of the different database systems and APIs that may be involved. A last type of transparency is transaction transparency. There, the DBMS transparently performs distributed transactions involving multiple nodes as if they were transactions in a standalone system. Query optimization becomes even more complex if queries are to be executed on data distributed over multiple nodes or locations. Ideally, location and fragmentation transparency are guaranteed by the DBMS, but even then, the optimizer should not only consider the elements of a standalone setting, such as availability of indexes, sizes of the tables, statistics on data usage and query execution, but also the properties of the respective fragments, communication costs, and the location of the data in a network. Also, the necessary metadata may be distributed. Based on these characteristics, both global, across all nodes, and local, within a single node, query optimization are needed. Usually, distributed query processing involves 4 steps: query decomposition, data localization, global query optimization, and local query optimization as illustrated here. The first and fourth step also exist in a standalone environment. The second and third step are particular to a distributed setting. In the query decomposition step, the query is first analyzed for correctness. Syntax and data types are verified, and column and table names are validated against the metadata in a catalog. The query is then represented in relational algebra and transformed into a canonical form, which is most appropriate for further processing. The data localization step entails the transformation of the query into a fragment query. The database fragments subjected to the query are identified as well as their locations. Several reduction techniques are applied in such a way that fragments that are guaranteed to contain no data that satisfies the query predicate are omitted from the fragment query. In this way, unnecessary processing is avoided where possible. During the global query optimization step, a cost model based on statistical evidence is used to evaluate different global strategies for query execution. The strategy with the lowest predicted cost is selected. The results of the previous step determine which operations should be performed on which location. For each of these local operations, a local query optimization step determines the optimal strategy for local execution. Let's illustrate the complexity of distributed query processing using an example. Without a doubt, the most crucial element is the global query optimization step. The example represents a situation where we want to retrieve all purchase order numbers and the names of the suppliers associated with the purchase orders. The database is distributed over 3 locations. All supplier data are in location 1. The purchase order and product data are maintained in location 2, and all other data are stored in location 3. The query originates from location 3, which is also where the query results should be delivered. We assume a share-nothing architecture. The figure contains some quantitative and statistical data that further describe the situation. Suppose the optimization criterion is minimal network traffic, and for simplicity, let's assume that each fragment corresponds to an individual table. We evaluate 4 possible strategies. Strategy 1. All tables are copied to location 3, which is also the location where all querying is performed. The total data transport amounts to 1000 times 84 plus 3000 times 16 bytes, which equals 132,000 bytes. Strategy 2. The supplier table is copied to location 2, where it is joined with the purchase order table. The query result is then sent to location 3. The data transport amounts to 1000 times 84 plus 3000 times 6 plus 30 bytes, which equals 192,000 bytes. Strategy 3. The purchase order table is copied to location 1, where it is joined with the supplier table. The query result is sent to location 3. The data transport amounts to 3000 times 16 bytes plus 3000 times 6 plus 30 bytes, which equals 156,000 bytes. Strategy 4. This strategy illustrates the semi-join technique. Here, projections are used to reduce tables before sending them over the network and joining them with other tables. In location 2, a projection operation is executed to yield all numbers of suppliers associated with a purchase order. We estimate this operation will yield 2000 supplier numbers. These numbers are copied to location 1, where a join operation is executed to combine the supplier numbers with the corresponding supplier names. This intermediate result is copied to location 2 to process the query further. The final result is then sent to location 3. Here, the data transport amounts to only 200 times 4 plus 200 times 4 plus 30 plus 3000 times 6 plus 30 bytes, which equals 115,600 bytes. If we only consider the 4 strategies mentioned above, and the optimization criterion is network traffic, the 4th strategy will be chosen. However, whereas the semi-join reduces the network traffic, a higher processing cost is incurred. Therefore, other strategies may be preferable if an optimization criterion other than network traffic is applied. There exists a large gamut of techniques to coordinate transactions in a distributed setting. In what follows, we elaborate on tightly versus loosely coupled settings, primary site and primary copy 2PL, distributed 2PL, two-phase commit protocol, optimistic concurrency, and loosely coupled systems, and compensation-based transaction models. Distributed transactions entail distinct sub-transactions at individual nodes or locations with a certain measure of autonomy. We speak of a global transaction coordinator and local participants in the distributed transaction. In a tightly coupled setting, the interdependence between participants and central control are substantial. The distributed transaction is required to have roughly the same asset properties as the transactions in a standalone setting. Such tight coupling is typically paired with synchronous communication between the transaction participants. Database connections remain open for the entire interaction. However, mobile devices, web services, and programming models geared towards loose coupling, such as .NET, also brought about the need for less tightly coupled distributed transaction paradigms. The interactions are based on asynchronous messaging and locally replicated data. Cached local updates are only synchronized periodically with the global system. Database connections are opened just long enough to synchronize the data or to execute a query and retrieve the results, but are closed immediately afterward. Loosely coupled paradigms often apply some form of optimistic concurrency rather than a pessimistic protocol. In a distributed but tightly coupled setting, many concurrency control techniques from a standalone database system are still applicable. Most of these techniques rely on locking. Three well-known approaches are primary site 2PL, primary copy 2PL, and distributed 2PL. Primary site 2PL comes down to applying the centralized two-phase locking protocol in a distributed environment. A single lock manager is responsible for lock management across all locations. The lock manager applies the rules of 2PL, so serializability is guaranteed. It informs the coordinator when the required locks can be granted. Based on that, the coordinator will instruct the transaction participants to execute their sub-transactions. A participant that has completed processing all its sub-transactions operations will notify the coordinator, who then instructs the central lock manager to release the corresponding locks. The biggest advantage of primary site 2PL is its relative simplicity. In contrast to other solutions such as distributed 2PL, no global deadlocks can occur. An obvious disadvantage is that the central lock manager may become a bottleneck. There is no local autonomy. Individual nodes cannot perform any local transactions without support from the central lock manager. Concentrating all locking activities with one node may also undermine reliability and availability. An extension of primary site 2PL is primary copy 2PL, which aims at further reducing the aforementioned disadvantages. Here, lock managers are implemented at different locations and maintain locking information pertaining to a predefined subset of the data. All requests for granting and releasing locks are directed to the lock manager responsible for that subset. In this way, the impact of a particular location going down will be less severe than with primary site 2PL, since only a subset of the data and transactions will be affected. With distributed 2PL, every site has its own lock manager, which manages all locking data pertaining to the fragments stored on that site. For global transactions that involve updates at n different sites, there will be n locking requests, n confirmations about whether the locks are granted or not, n notifications of local operations having completed, and n requests to release the locks. In this way, location autonomy is respected, but there is a considerable increase in message exchanges, particularly so if the global transaction involves many participants. Also, global deadlocks and other undesirable circumstances may occur, which require precautions to be included as additional rules to the basic 2PL. As long as the database has no replicated data, applying the basic 2PL protocol guarantees serializability. Since the local schedules will be serializable, the global schedule, which is nothing more than the union of the local schedules, will be serializable as well. The latter no longer holds if certain data are replicated over different locations. In this case, the 2PL protocol must be extended. This is illustrated here. The example represents a schedule with two global transactions, T1 and T2. Both transactions update the value of the same account X. This value is replicated as it is stored on both the locations L1 and L2. T1 subtracts 50 from the amount on account X using the subtransactions T1.1 in L1 and T1.2 in L2. T2, on the other hand, doubles the amount on account X using the subtransactions T2.1 in L1 and T2.2 in L2. The order in which the operations are executed is important. The global schedule, as shown in the example, results in inconsistent data. If the initial value of x is, say, 100, then the final value of x in L1 is 150, whereas it is 100 in L2. Still, the local schedules by themselves are serializable. The problem is that both schedules serialize T1 and T2 in a different order. This illustrates that to guarantee global consistency, an additional requirement needs to be imposed apart from the serializability of the local schedules. This requirement stipulates that conflicting operations should be executed in the same order across all schedules. The second issue pertaining to 2PL is that it can give rise to global deadlocks. A global deadlock spans several locations. Consequently, it cannot be detected by individual local lock managers. Deadlock detection in distributed 2PL requires the construction of a global wait for graph besides the local graph. A schedule is only deadlock free if not only the local graphs but also the global graph contains no cycles. This figure illustrates this. Two transactions, T1 and T2, process a money transfer between account X and account Y. The account data are stored in location L1 and L2 respectively. Transaction T1 transfers 50 from account X to account Y using subtransactions T1.1 and T1.2, whereas transaction T2 transfers 30 from account Y to account X using subtransactions T2.1 and T2.2. Although the schedule complies with 2PL, a global deadlock will occur. Whereas there are no cycles in the respective local wait for graphs, the global wait for graph, which combines the local ones, does contain a cycle denoting a global deadlock. There are different approaches to detect global deadlocks. For example, one location can be chosen as the central site to maintain the global wait for graph. All local lock managers will periodically inform the central site of changes in their local wait for graphs to update the global wait for graph. If one or more cycles are detected, the local lock managers will be informed accordingly, and victim selection will determine which transaction or transactions to abort and roll back to resolve the global deadlock. The mechanism for transaction commit and abort should guarantee that the global transaction can only attain a committed or aborted state if all its subtransactions have attained the same state. Also, care should be taken that individual locations that participate in a global transaction cannot get blocked because of a communication infrastructure malfunction or other calamity. The two-phase commit protocol, 2PC, was developed specifically to support transaction recovery in a distributed environment. The protocol derives its name from the fact that global transaction completion involves two phases: a voting phase, in which all transaction participants vote about transaction outcome, and a decision phase, in which a transaction coordinator makes the final decision about the outcome. The two-phase commit protocol is illustrated here. In phase 1, the coordinator of the global transaction sends a prepare message to all transaction participants. The coordinator then waits until all participants have responded or until the timeout period has passed. Upon receiving a prepare message, each participant assesses whether it can commit the transaction. If it is, then a commit vote is sent to the coordinator. In the opposite case, the participant sends an abort vote to the coordinator, after which it immediately aborts the local transaction. In phase 2, the votes are counted by the coordinator and a final decision is made about transaction outcome. If all participants voted commit, the coordinator decides to execute a global commit. It sends a global commit message to all participants and enters the committed state. If at least one participant voted abort, the coordinator decides to abort the transaction globally. It sends a global abort message to all participants and enters the aborted state. Each participant then locally executes the global decision, commit in the first case and abort in the second, and returns a confirmation to the coordinator. Finally, the coordinator completes a transaction using an end transaction mark on the log file. The 2PC protocol is supplemented by two additional protocols, a termination protocol and a recovery protocol. Given a distributed setting, care should be taken that neither the coordinator nor the participants can end up in an endless state, waiting for a message that will never come because of a communication malfunction or because the party that should send the message had faulted. Therefore, a site will wait no longer for incoming messages than for a fixed timeout period. If a timeout occurs, it will invoke a termination protocol, also known as timeout protocol, which describes how to react to the timeout. If the timeout was caused by a calamity at one of the other locations, a recovery protocol describes how the faulty site should correctly resume operation after its malfunction. Optimistic concurrency protocols resolve conflicts before transaction commit, typically with an abort and rollback of the conflicting transaction or transactions. Optimistic concurrency can be advantageous in many distributed settings, where the loose coupling between the respective participants in a distributed transaction would render other approaches inappropriate. Tightly coupled distributed systems often apply a pessimistic concurrency protocol, enforcing global transaction serializability by, across all participants, placing locks on the database objects that participate in the global transaction. Conflicting operations of other transactions are postponed until the locks are released. In a tightly coupled environment, transactions are typically sufficiently short-lived so as to not hold any locks for longer periods. A transaction either commits in a short time span, or the transaction coordinator and the other participants are notified promptly that a participant is not available or will not be able to commit its sub-transaction, so the global transaction can be aborted and locks can be released across all participants. The situation is different in a loosely coupled setting, characterized by asynchronous communication and unpredictable response times of the transaction participants. Therefore, pessimistic concurrency is mostly inappropriate and at least not very scalable in such a context. Hence, loosely coupled distributed systems often apply an optimistic concurrency protocol. A typical application of loose coupling and optimistic concurrency is the disconnected database paradigm as applied in amongst others Addo.NET datasets. In this context, locks are only held during the brief period when a database connection is open to exchange data between the database and the dataset. However, whereas optimistic concurrency may considerably increase transaction throughput and overall data availability in a loosely coupled setting, because of the absence of locks, there is also a downside. For example, suppose application A1 reads data from a database into a dataset and then closes the database connection. After that, the data in the disconnected dataset can be processed and possibly updated locally. If these updates are to be propagated to the database afterward, a new connection is opened, again only for the brief time of the data exchange. However, there is no guarantee that the original data in the database was not altered by another application, A2, in the meantime. There, the updates by A1 will be rejected because they would override A2's updates, which are unknown to A1, resulting in a lost update. Note, it would not be a solution to log the original data in the database either, since in a disconnected setting, the DBMS would not know when, if ever, application A1 will reconnect to release the logs, which is obviously unacceptable from a data availability and throughput perspective. There exist different techniques to detect conflicting updates in an optimistic concurrency setting. A first possibility is the use of timestamps. In this approach, a timestamp column is added to any table that is open to disconnected access. The timestamps indicate the time of the most recent update of a row. If an application A1 retrieves rows from the database and then disconnects, the timestamp column is copied. At the moment when the application attempts to propagate its updates to the database, the timestamp associated with an updated row is compared to the timestamp of the corresponding row in the database. If both timestamps don't match, it means that the row in the database was updated by another application A2 in the meantime, so the update by A1 will be refused. If the timestamps match, the updated row can be propagated safely to the database, and a new timestamp value is stored in the database for the corresponding row. A second possibility, which is the default technique in an ADO.NET dataset, is to store two versions of each row in the disconnected entity, a current version and an original version. The original version contains the values as they were read from the database. The current version contains the values as they were possibly affected by local updates in the dataset which are not yet propagated to the database. Once the dataset attempts to propagate updates to the database, for each locally updated row, the original values are compared to the values of the corresponding row in the database. If the values are identical, the row in the database will be updated with the current values of the corresponding row in the dataset. If they are not identical, it means that the row in the database was updated by another application in the meantime, and the update by the dataset is rejected. The latter approach is illustrated here. Suppose an ADO.NET dataset was generated based on the rows in a database table, myTable, consisting of the columns column1, column2, and column3. An update to the database table will only be accepted if the column1, column2, and column3 values in the database are equal to the add_original values in the dataset. In that case, the database row will be updated with the corresponding add_current values of the dataset. If the values are not equal, which means that the rows in the database were already updated by another party, the where condition is not satisfied and no data will be updated. A loosely coupled environment also affects recovery and how transaction atomicity is to be guaranteed. Many loosely coupled settings, such as web service environments, are characterized by long-running transactions. The duration of such transactions depends on the asynchronous interactions between participants in a business process and can be extensive, as the name suggests. Let's consider the example of a travel agent web service where customers can book trips that consist of flight tickets and a hotel booking. The travel agent service, in its turn, calls upon respectively an airline service and a hotel service to perform its task. In this context, it acts as the coordinator of a global transaction, in which the airline service and the hotel service are participants. Suppose the transaction is initiated by choosing a destination. It is possible that the customer then takes time to decide on an airline. Maybe the hotel service is temporarily unavailable. The global transaction will only be completed if all participants have done their part, but because of the loosely coupled asynchronous character of the interaction, this may take from minutes to hours or even days. Enforcing actual asset properties in such a context would be next to impossible. Also, it would be unadvisable to use a pessimistic concurrency protocol, because locks might be held for as long as the long-running transaction is active, with a dramatic impact on data availability and throughput. On the other hand, pure optimistic concurrency may be inappropriate in this situation, because a coordinated rollback across participants representing independent organizations would be hard to realize if a concurrency issue is detected after a long-running transaction has been active for an extensive amount of time. Here you can see our example of a travel agent web service illustrated. In the case of long-running transactions, a compensation-based transaction model is often more appropriate. It allows for undoing local effects of a transaction if the global running transaction is unsuccessful. The latter could be for reasons of transaction failure, but just as well because of issues at business process level. An asset transaction would require the entire transaction to be rolled back, including the successful hotel booking. However, a compensation-based transaction mechanism abandons the atomicity property of the long-running transaction. Local subtransactions within a single participant remain atomic and are committed as soon as possible without waiting for a global commit notification. In this way, all locks held at that individual participant's premises can be released, with a positive effect on local transaction throughput, and even more important, it makes the participants less dependent on one another with respect to locking and data availability. A compensation-based transaction mechanism will require each transaction participant to define its transaction-sensitive operations in pairs, with the second operation specifying a new local transaction that cancels out the effects of the first one. In other words, it literally compensates for the first transaction. Let's examine the example here. The global book trip transaction, which is coordinated by the travel agent service, is long-running. Therefore, it may take some time to complete, and therefore it is undesirable to enforce atomicity. The transaction consists of two sub-transactions, book hotel and book flight, which reside entirely with an individual participant. Each participant will attempt to locally commit its sub-transaction without awaiting the outcome of the global transaction. Let's assume that the hotel service completes its sub-transaction. The book hotel transaction is committed, all locks pertaining to the sub-transaction are released, and the hotel service notifies the transaction coordinator of its successful completion of the sub-transaction. However, suppose the airline service cannot commit the transaction, for example, because there are no more flights available. It will abort and roll back the local transaction and notifies the transaction coordinator accordingly. However, a global rollback is no longer possible, since one of the local transactions was already committed. Instead, a compensation-based transaction mechanism will require each transaction participant to define its transaction-sensitive operations in pairs, with the second operation specifying a new local transaction that cancels out the effects of the first one as mentioned before. In this example, the hotel service will specify a book hotel operation along with a compensate book hotel operation, whereas the airline service specifies a book flight and a compensate book flight operation. If the local book hotel transaction was committed, but the global transaction fails, then the compensating operation, compensate book hotel, will be invoked by the transaction coordinator. This compensating operation will not roll back the local transaction as such. This would not be possible since it was already committed, but will instead induce a new transaction that somehow makes up for the changes made by the first transaction. A compensation-based transaction model will require that for each transaction-sensitive operation OI offered by a service, a compensating operation CI is specified. If a global transaction that invoked OI is aborted, CI will be invoked by the transaction coordinator. The implementation of CI should be hand-coded by the developer. It is no automated feature offered by the DBMS. In this way, the global, long-running transaction is no longer atomic. Note, however, that traditional asset properties can still be enforced on the short-lived local subtransactions as induced by OI and CI. Compensation is the default transaction mechanism of languages such as WS-BPEL, which define long-running processes as orchestrations of individual web services. Finally, it is important to mention that a compensation-based transaction model does not guarantee transaction isolation. In some loosely coupled settings, compensating transactions are the only technically feasible alternative, whereas in others, the trade-off can be considered between enforcing asset properties and higher performance. An approach with pessimistic concurrency is preferable, where many concurrent updates to the same data subsets are expected, especially if data consistency is important. In other situations, one will be prepared to sacrifice a certain measure of consistency if this improves throughput, data availability, and scalability. There, optimistic concurrency and/or compensation can be considered, especially if the concurrent access to the same data subsets is rather limited or if the read operations largely outnumber the write operations. The trade-off between consistency and performance is also very pertinent to the divide between traditional relational databases and NoSQL databases. In particular, NoSQL databases often propose an alternative transaction paradigm, base transactions, in contrast to the asset paradigm known for a relational database setting. A new wave of database management systems under the common denominator of NoSQL databases aims to overcome the capacity limitations of RDBMSs and cater for the storage of big data. Although these are very diverse in nature and approach, there are some principles regarding data distribution and distributed transaction management that are prevalent in many of them. In what follows, we discuss horizontal fragmentation and consistent hashing, the CAP theorem, base transactions, multi-version concurrency control in vector clocks, and quorum-based consistency. Many NoSQL databases apply some form of horizontal fragmentation, referred to as sharding. The horizontal fragments, called shards, are allocated to different nodes in a database cluster with a hashing mechanism applied to the data item's key. The sharding, which usually also entails a level of data replication, allows for parallel data access across the respective nodes, supporting massive amounts of data and very high volumes of read and write operations. Therefore, many NoSQL DBMSs approach linear horizontal scalability, which means that the performance increases nearly linearly with the number of nodes in the cluster. In addition to the performance, the combination of sharding and replication also yields high availability, with the workload being redistributed over the other nodes in case of failure of a node or network connection. The same levels of horizontal scalability and availability would never be achievable by traditional DBMSs executing ACID transactions over a cluster of nodes. The CAP theorem was originally formulated by Eric Brewer and states that a distributed system can exhibit at most two of these three desirable properties. Consistency, all nodes see the same data and the same versions of these data at the same time. Availability, every request receives a response indicating a success or failure result. Partition tolerance, the system continues to work even if nodes go down or are added. The distributed system can cope with it being divided into two or more disjoint network partitions due to node or network failure. A standalone system can provide both data consistency and availability with ACID transactions. Traditional, tightly coupled distributed DBMSs will often sacrifice availability for consistency and partition tolerance. Many NoSQL database systems will give up on consistency, the reason being twofold. First, in many big data settings, unavailability is costlier than temporary data inconsistency. For example, it is far preferable that multiple users get to see partially inconsistent versions of the same social media profile, for example with or without the latest status update, than having the system unavailable until all versions are synced and all inconsistencies are resolved. In case of node or network failure, the transaction will be executed, even if one or more nodes cannot participate, yielding a possibly inconsistent result or database state. Second, even if no failure occurs when executing the transaction, the overhead of locking all the necessary data, including replicas, and overseeing that consistency is guaranteed over all nodes involved in a distributed transaction has a severe impact on performance and transaction throughput. The CAP theorem can also be criticized. As became apparent from the previous discussion, it is not only the actual occurrence of network partitions that will result in the choice to abandon consistency. The performance degradation, induced by the overhead of mechanisms that enforce transactional consistency, is often the true reason to abandon perpetual consistency. This overhead is further increased by the data replication that is necessary to guarantee availability and to be prepared for failures. This overhead exists even when no such failures occur. Also, one could argue that availability and performance are essentially the same concepts, with unavailability being an extreme case of high latency and low performance. Therefore, in many high volume settings, the real trade-off is between consistency and performance. Obviously, the result of this trade-off will be different, depending on the setting. A bank will never allow for its customers to receive an inconsistent overview of their savings. Let me do that again. Obviously, the result of this trade-off will be different depending on the setting. A bank will never allow for its customers to receive an inconsistent overview of their savings account status just for the sake of performance. Although many NoSQL databases make a different trade-off between consistency and availability or performance than more traditional DBMSs, they do not give up on consistency altogether. They position themselves on a continuum between high availability and permanent consistency, where the exact position on this continuum can often be configured by the administrator. This paradigm is called eventual consistency. The results of a database transaction will eventually be propagated to all replicas, and if no further transactions are executed, then the system will eventually become consistent, but is not consistent at all times, as is the case with ACID transactions. To contrast this approach to ACID transactions, this transaction paradigm was coined as base transactions. Base stands for basically available, soft state, eventually consistent. In other words, basically available, measures are in place to guarantee availability under all circumstances, if necessary, at the cost of consistency. Soft state, the state of the database may evolve, even without external input, due to the asynchronous propagation of updates throughout the system. Eventually consistent, the database will become consistent over time, but may not be consistent at any moment, and especially not at transaction commit. Write operations are performed on one or at most a few of the replicas of a data item. Once these are updated, the write operation is considered as finished. Updates to the other replicas are propagated asynchronously in the background, so eventually all replicas receive the update. Read operations are performed on one or only a few of the replicas. If only a single replica is retrieved, there is no guarantee that this is the most recent one, but the eventual consistency guarantees it will not be too out of date either. If a read operation involves multiple replicas, these may not necessarily be consistent with one another. There are different options to resolve such inconsistencies. The DBMS contains rules to resolve conflicts before returning the retrieved data to the application. This often involves the use of timestamps, such as last write wins, which means that the most recently written version is returned. The burden of conflict resolution is shifted from the DBMS to the application. Here, the business logic can determine how conflicting replicas of the same data item can be reconciled. With base transactions, conflict resolution does not necessarily happen at the moment of writing the data, but may be postponed until the data is actually read. This approach is inspired by the concern of availability and transaction throughput. For example, it would be unacceptable for a web store that the inability to write to the database induces missed sales transactions. Rather than postponing the write operation until the risk of conflicts is mitigated, a new version of the data item is created with the updated value. Meanwhile, another user or application may be inducing another write, resulting in yet another replica of the same data item. As a consequence, the DBMS may contain multiple inconsistent versions of this data item. Conflict resolution between these versions is postponed until the data is actually retrieved. The concurrency protocols that sustain this approach are called MVCC, multi-version concurrency control. Such protocols are typically based on these principles. A read operation returns one or more versions of a data item. There may be conflicts between these versions, which are resolved by the DBMS or the client application. A write operation results in the creation of a new version of a data item. A more elaborate kind of timestamps called vector clocks are used to discriminate between data item versions and to trace their origin. Each version of a data item is associated with such a vector clock. Versions of a data item that are obsolete according to their vector clock are garbage collected. A vector clock consists of a list of node counter pairs, with the node referring to the node that handled the write of that version and the counter denoting the version number of writes by that node. In this way, the entirety of vector clocks associated with versions of a data item represents the lines of descendants of the respective versions. A read operation retrieves all conflicting versions of a data item, with the versions vector clocks. A write operation creates a new version of a data item with a corresponding vector clock. If all counters in a version's vector clock are less than or equal to all counters in another version's clock, then the first version is an ancestor of the second one and can safely be garbage collected. Otherwise, both versions represent conflicting versions and should be retained. They may be reconciled afterward. An example is shown here. Suppose a client stores a new data item D into the database. The write is handled by node N1, which creates a first version D1 of the data item. This results in the vector clock N1, 1. Then, the client updates the data item and the write is handled by the same node N1. A new version D2 of the data item is created and the vector clock becomes N1, 2 since the same node N1 has created a second version. According to the vector clock, D2 is a descendant of D1 and therefore D1 can be garbage collected. Then, once more, the client updates the data item, but now the write is handled by a different node, N2. This results in a third version, D3 of the data item, which descends from D2 and which is the first version written by N2. The vector clock therefore becomes N1, 2, N2, 1. Now suppose in the meantime another client Now suppose in the meantime another client reads D and receives version D2. The client updates the data item and the write is handled by yet another node N3. This results in a version D4 which is a descendant of D2. The vector clock becomes N1, 2, N3, 1. Note that D2 can be garbage collected because it is superseded by both D3 and D4 and is also represented in the respective vector clocks. However, both D3 and D4 need to be retained. Although they have a common ancestor in D2, they do not descend from one another, and both D3 and D4 contain updates that are not reflected in the other. This is also represented in their vector clocks. However, at some point, both versions will be read and reconciled by a client or by the DBMS. The new version, D5, will be a descendant of both D3 and D4. Suppose the write is handled by N1 again. The vector clock then becomes N1, 3, N2, 1, N3, 1. D3 and D4 can now be garbage collected. Many NoSQL database systems provide the administrator with the means to position the system on a continuum between high availability and permanent consistency. This position can be configured by manipulating the parameters in a quorum-based protocol. Quorum-based protocols essentially enforce consistency between replicas of the same data item using three configurable parameters, n, r, and w, with r less than or equal to n and w less than or equal to n. N represents the number of nodes to which a data item is replicated. The higher n, the higher the redundancy, and hence the smaller risk of unavailability or data loss. A higher n also allows for more parallelism, but increases the overhead if one needs to keep all n replicas permanently consistent. R refers to the minimum number of nodes that should respond before a read operation for a data item can be considered as completed. The higher R is, the slower the read performance since the response time is determined by the slowest of these R nodes. A higher R increases the chance that the set of replicas returned by these R nodes contains an up-to-date version of the data item. W refers to the minimum number of nodes that should receive the update value before a write operation for a data item can be considered as completed. The higher W is, the slower the write performance since the response time is determined by the slowest of these W nodes. A higher W increases the number of nodes that contain an up-to-date version of the data item and therefore increases consistency of the database. By manipulating R and W, the database administrator can decide on the trade-off between performance and consistency, but also on the trade-off between read performance and write performance. A configuration with R plus 1 strictly bigger than n is guaranteed to provide at least one up-to-date replica with each read operation. Configurations with R plus W less than or equal to n will have better read and write performance, but it cannot be guaranteed that the result set of each read operation will contain an up-to-date replica. Some typical configurations are depicted here. 4 configurations are presented with each time n equals 3 and with varying r and w. The circles represent replicas of a single data item stored on node 1, node 2, and node 3, with a dark circle denoting an up-to-date replica and a light circle denoting an outdated replica. For the sake of simplicity, let's assume that the first node always responds after 100 milliseconds, the second node after 200 milliseconds, and a third node after 300 milliseconds. Let's also assume these figures hold for both read and write operations. In real-life situations, these values will fluctuate depending on the actual workload of every node. Configuration A represents a situation where both r equals 1 and w equals 1. A write operation is completed after a first node has received the updated value. This takes 100 milliseconds. A read operation is completed once the response from one node is received. This takes 100 milliseconds as well. However, the first responding node may not be the one with the most up-to-date replica of the data item, so the result may be slightly outdated. However, this may not be a problem in many big data contexts. Configuration B represents a situation where r equals 1 and w equals n. Now, a write operation is only completed after all 3 nodes receive the updated value. For the slowest responding node, this is after 300 milliseconds, so the write takes much longer than in configuration A. A read operation is still considered as completed once the response from one node is received, so the read time remains at 100 milliseconds. Since all nodes participated in the write and hence received the updated value, the response of even a single node is guaranteed to provide an up-to-date version of the data item. This configuration may be appropriate in settings with not too many writes, but the need for many fast reads, for example, if the database contains fairly stable product catalog data. Configuration C represents a situation where r equals n, w equals 1. A write operation is completed after a first node has received the updated value, so the write time is back to 100 milliseconds. Now, a read operation is only completed once the response from all 3 nodes is received, so the read time increases to 300 milliseconds. Since all replicas of the data item are retrieved with the read, the result set is guaranteed to contain the most up-to-date version next to more outdated versions. Upon every read, the conflicting versions can be reconciled by the DBMS or by the application. Write performance will be better than read performance, so this configuration may be appropriate if the DBMS needs to be always writable, for example, in order not to miss any sales transactions because of too slow response times. Configuration D represents a situation where both r equals 2 and w equals 2. A write operation is completed after 2 nodes have received the updated value, so the write time is 200 milliseconds. Now, a read operation is completed once the response from 2 nodes is received, so the read time amounts to 200 milliseconds as well. Since 2 out of the 3 replicas are retrieved with each read operation, and 2 out of the 3 nodes receive an up-to-date value with each write operation, the result set of each read is guaranteed to contain the most up-to-date version, possibly next to a more outdated version, although both versions in the result set could be up to date as well. The conflicting versions can be reconciled by the DBMS or by the application. Note that any of the 4 configurations can be most appropriate, depending on the context and the need for retrieving up-to-date versions of the data at all times and depending on the trade-off between read and write performance. However, configuration D, with w equals 2 and r equals 2, strikes a good balance between all concerns. As mentioned, a configuration with r plus w bigger than strictly bigger than n is guaranteed to provide at least one up-to-date replica with each read operation. This is the case in configurations B, C, and D. Configurations with r plus w less than or equal to n will have better read and or write performance, but it cannot be guaranteed that the result set of each read operation will contain an up-to-date replica. This situation was illustrated in configuration A, which had the best overall performance. In this chapter, we dealt with distributed databases and specifically focused on distributed transaction management. We started with the rationale behind distributed systems and data distribution and discussed different architectural setups. Then, we discriminated between horizontal, vertical, and mixed fragmentation and discussed data replication and different kinds of transparency. We overviewed the complexities of distributed query processing and query optimization. Finally, we introduced transaction paradigms for tightly coupled and more loosely coupled distributed settings, with examples of both pessimistic and optimistic concurrency. We focused on the extra coordination required to guarantee data consistency and transaction atomicity. Also, some paradigms sacrificed atomicity and or consistency to a certain extent to reduce overhead and improve transaction output. As an example, here are compensation-based protocols. An example here are compensation-based protocols. The chapter concluded with a discussion of the base transaction paradigm, which is often applied in a NoSQL setting and which can be complemented by multi-version concurrency control and quorum-based consistency. If you want more information on this, I'm happy to refer you to our book, Principles of Database Management. See the website at the bottom of my slide.